Hi guys, welcome to Chapter 6, Normal Probability Distributions. We're going to kind of see what the function of a normal probability distribution in real life is. That's what this is all about in this unit. So let's get started. So first thing we need to do is we need to look at two types of distributions of random variables. One's uniform, one's standard normal. We're also going to find the areas or probabilities under the curve for both the normal and standard distribution. This will tie into some of the calculus that you might do later on in life. And so the first thing we're going to find is the z-scores that correspond to the areas under the graph. And we're going to call the graph of any continuous probability distribution a density curve. That's its official name. And its area is going to have to equal 1. So uniform distribution. That's basically when your random variable has its value spread evenly over the shape or over the range of possibilities. That's basically a rectangular shape because your histogram, they're all going to be close to the same height. So the area under the graph of a continuous probability distribution, we already said that's going to be equal to 1. And there's a relationship between the area and the probability. So the probabilities can be found by finding the area under the graph. Remember, if it's rectangular in shape, the area is the height times the width. Because it's a rectangle. So here's an example. During a certain period of time at JFK Airport in New York City, passengers arriving at the security checkpoint have waiting times that are uniformly distributed between 0 and 5 minutes. So here's a graph of it. What properties do we see? Well, first thing is, all of the different waiting times are equally likely. That's why they're all the same height. And waiting times can be anywhere between 0 and 5 minutes. And if we assign the probability of 0.2 to the height of the vertical line, the enclosed area is exactly 1. Remember, we want to have the area under the curve to be 1. So we divide each of these 1, 2, 3, 4, 5. So 1 divided by 5 is 1/5. That's 0.2. That means each one of them's probability is 0.2. Let's look at another example. All right, here we are. Uniform distribution again given. And we are going to find the probability of a randomly selected passenger that has these waiting times. So the probability of at least 2 minutes. So probability of at least 2 minutes. So 2 minutes. There he is. And then there's 3, 4, 5. So at least 2 would be here and above, right? At least 2. That's 1, 2, 3 rectangles over there. So that's 0.2 is their height times 3 wide is a probability of 0.6. So 60% probability that you're going to be waiting at least 2 minutes. Now let's try our next one. Greater than 3 minutes. So our probability is greater than 3 minutes. So here's 3 minutes. And that means that's everybody over here, greater than 3 minutes. That's 2 spots. So that's 0.2 high times 2 spots is a probability of 0.4, or 40%. They're going to be waiting more than 3 minutes, a 40% probability. Our next one, less than 4 minutes. Probability of less than 4 minutes. Okay, here's 4. That's this way, less than. So that's 1, 2, 3, 4 rectangles. So 0.2 times 4 is 0.8. So 80% probability you're going to be waiting less than 4 minutes. And then D, in between 2 and 3 minutes. So that's this one here, which is 1 rectangle. So probability between 2 and 3 is 0.2 times 1 rectangle, which is 0.2. So 20% probability you'll be between 2 and 3 minutes waiting time. So that's uniform, and it's real easy because it's just area of a rectangle. Normal distribution. You remember this curve over here? That's the normal bell-shaped curve. He's symmetric. He's beautiful. Mu is your middle mean, and the sigma is your standard deviation. You do have a nice, beautiful formula for the normal distribution. In this class, you will not be using this. However, if you take some further probability and statistics classes, you will be knowing this formula because you'll be using it in calculus. So, something to look forward to, guys. So, some properties of the normal distribution. Well, we've already discovered it is bell-shaped. Remember, the uniform one was kind of like a rectangle. The mean is mu, and it's at 0. The standard deviation, that's sigma, is equal to 1. Every normal distribution has these properties. Now here's our lovely normal distribution. Again, since it's a density curve, it's going to be still having a probability or area underneath equal to 1. So what we're going to do is we're going to have z-scores along the x-axis. It makes it easier on us. Notice that z-score of 0 is the mu, and then out each direction we have the positive and negative z-scores, just kind of reminding you of this. Z-scores are the number of standard deviations above or below the mean. Remember, our mean is 0, our standard deviation is 1, so that makes the standard normal distribution. The total area under the density curve is equal to 1. Now, here's where we're going to be talking about left, right, things like that. So the cumulative left region. When you're working with a normal distribution, be careful that you're not confusing the z-scores on the areas. So when we read the normal distribution, we obviously read, in this case, right to left. Here's the z-score down here, and then here's the area over here. It's area to the left of the z-score. Now, if we have area between two boundaries, again, here's a lower z-score, here's an upper z-score, and we're looking at the area between them. So, example 3, find the area to the left of the value. A bone mineral density test can be helpful in identifying the presence or likelihood of osteoporosis. That's a disease causing bones to become more fragile and more likely to break. The result of a bone density test is commonly measured as a Z-score. The population of Z-scores is normally distributed with a mean of 0, standard deviation of 1, so that means it's a standard normal curve. That's him down there with all the little people in it. So these test results meet the requirements. And the graph of the bone density is shown below. A randomly selected adult undergoes a bone density test. Find the probability that this person has a bone density test score less than 1.27. So what we're wanting to know is the probability that this person has a Z-score less than 1.27. So we've got one, remember zero's here in the middle, so 1.27 is going to be something like this. There's 1.27. So what we're looking for is the area to the left of 1.27. So we're going to go to the table for our cumulative area to the left of the Z-score and look up 1.27. So when we go to our table, we get 0.8980. That's the probability. So 89.8% probability that this person's going to have a Z-score less than 1.27. Now, if I wanted to use my calculator, that's a normal, because this is a normal distribution, CDF, because it's cumulative, it's less than, of the smallest number. Remember, your calculator has some issues with it. We talked about this in the last unit. Our Z-score, 1.27. Our mean and our standard deviation. And it would also tell us that it's 0.897, 9576, 193, or in our case, 0.8980 when you round it. So you can use either the table, this is where I got this from, or you can use your calculator, one or the other. I don't care which one you guys use. I like the calculator because it's faster. All right, let's try another. So we need to find the area to the right of a value. Using the same bone density test from example 3, we're going to find the probability that a randomly selected person has a result above -1. And above -1 is considered to be normal, by the way. So remember, 0 is going to be in the middle, so -1 is going to be over here. So we're going to want everybody above -1. Well, how do we do that? So the probability that your Z-score is above -1 is the same as 1 minus the probability that your Z-score is less than -1. This is less than -1, so it's 1 minus that would give you the red part. So if I go to my table, 1 minus the probability less than -1 is 0.1587. So I subtract that, and I get 0.8413. Or if I want to use my calculator, I would do 1 minus the normal CDF of my negative with all my 9s, comma, -1 and 0 and 1 because it's standard normal, and it's going to tell me the same thing, 0.8413. And my calculator gives a little bit more numbers, but again, we round. Okay, what if we want the area between two values? This one's a bone density test reading between -1 and -2.5. Indicates that they have osteopenia, which is some bone loss. So we need to find that probability that somebody has that. Find the probability that somebody's between -1 and 2.5. So here's -1, -2, -3. So we want to know who is between here. So we want to do that. So a way that we can do that with using the tables, probability someone's between -2.5 and -1 is the probability that someone's less than -1 minus the probability that someone is less than -2.5. Now make sure we got that right. Here's less than -1 is all this, okay? And less than -2.5 would just be this. So that would leave, if you take off the green from the yellow, it would leave the red part. That's what they're trying to say. So how do we do that? We go to our table, find the probability less than -1. That's 0.1587 minus probability of less than 2.5, just 0.0062 from my table. I subtract them, I get 0.1525 for my answer. Or if I want to use my calculator, it's a normal CDF. My lower value is -2.5. My upper value is -1.0. And it's standard normal, so 0, 1. Again, I get the same answer. So I want you to know that you could use either the calculator or your tables. Here is some practice problems for you guys to practice if you would like a little extra. Each one of these, I'm going to go ahead and put the answers in here for you so that if you do check or want to practice them, you can. This one, the answer is 0.6700. This one's answer is 0.8508. And this one's answer is 0.6992. Again, this is up to you. If you need extra practice, feel free to work on them. Now we're going to go backwards. We're going to find the z-scores if we know the area. So here we have the area, and we want to know the z-score down here kind of thing. So we're going to use our same bone density test scores that we had. The scores are normally distributed with a mean of 0, standard deviation of 1. So that means that these are standard normal distribution. So we can use our tables. We're going to find the bone density score corresponding to the 95th percentile. That means the area is 0.95. So we want this z-score because we know the area in here is 0.95. So how do we do that? We want the probability of z being less than a to equal 0.95. So we're going to look in our table for 0.95 as an area, and we notice that it's halfway between 1.64 and 1.65. So z from our table is 1.645. So that's my z-score. Or if I want to use the calculator, which I prefer, since this is a normal distribution and we're going backwards, we call that the inverse norm. And our area is 0.95. Our mean and standard deviation are 0 and 1. And since we want what's to the left of it, we choose the word left. And look at this. It tells us what our z-score is using the calculator. So use whatever method you like to use. I prefer the calculator, but there are tables that you can use. Okay, so if we use that same bone density test score, then we have the normal distribution here. We're going to find the bone density test score that separates the bottom 2.5% and find the score that separates the top 2.5%. So 2.5%, change that to a decimal. So we're trying to find the top and bottom 2.5%. Those are going to be your really tiny ones. So like, this is going to be like 0.025 and 0.025 for the area. And these tips. And we want those z-scores. Okay, that's what we're looking for. So the probability that our z is less than a equals 0.025. So we go to our table, look for the area. Plus we also want the other one. The probability of our z is greater than a. From our chart, if we go and look those up, we get z in this case is negative 1.96. And over there for the other one above it, that's z equals positive 1.96. Or we could use our calculator and do the inverse norm. And our amount is 0.025, 0, 1, and left. And inverse norm, our area is 0.025. Well, that was not 0.025. 0, 1, and right. In doing so, this one will give us our negative 1.96 when you round it, and this one will give us our positive 1.96 when you round it. Okay, again, here's the areas given, and you know they're a standard normal, and they want to know your z-scores. I'm going to let you practice finding them, and here is the answers. This one, the z-score is at 1.23. This one, the z-score is at negative 0.51. So again, you can either use the chart or you can use the calculator, the inverse norm, whichever you're most familiar with and like better, to get these answers and practice on your own. Now, a critical value. For a standard normal distribution, the critical value is the z-score on the borderline separating the z-scores that are significantly low or high. And we call that z sub a. That's the z-score with an area of alpha. That's the critical value to the right. So let's talk about that. Finding critical values. Find the value of z with a critical value 0.025. That means alpha is 0.025 in the expression z alpha. All right. So what did we just read? We know that alpha is 0.025, and that's the area to the right. But we use a chart, so we need the area to the left. So we're going to do 1 minus alpha, and that's going to give us 0.975. So we want the probability that z is less than alpha is equal to 0.975. And when we look at our chart, that's z is the score 1.96. Now, how will we find this using the calculator? Same way we've been doing. The inverse norm of our area, which is 0.975 for a 0, 1, and left, will tell us our z-score is at 1.96. So we're finding that value, our z, is at 1.96. All right, so that means you're going to have to do these. We're going to practice them. If we have a z at a critical value of 0.10, remember that's to the right. So that means alpha is 0.1, but that's to the right. We want the left. So 1 minus alpha is 0.9. So our probability of z less than a equaling 0.9 in our chart will tell us z is 1.28. Or if we wanted to use the calculator, we could have done the inverse norm of 0.901 and the word left. And it still would have told us that z is 1.28. Now again, I want you to try some of these. I want you to find the z-score for number 42 over here with an alpha 0.02. And the answer you're going to end up with is 2.05. So give this one a try. Make sure you can do it too. Using the calculator or the chart, I don't care which way. Now into 6.2, we're going to look at some applications of normal distributions. So the first thing we have up here is a conversion from a z-score from a non-standard normal distribution to a standard normal distribution. So heights of men are normally distributed with a mean of 68.6 and a standard deviation of 2.8. Good for you men. You're that tall with a standard deviation of that. Find the percentage of men who are taller than a shower head at 72 inches. So we need to look at this. Is this a standard normal distribution? No, because the mean is not 0. The standard deviation is not 1. So we have to use our little formula that we were just given. So our z is 72 minus our mean over our standard deviation, which in this case is 1.21. So now what we're asking is we want taller than that, so probability that our z is greater than 1.21. Well, 1.21, if there's 0, there's 1. So the 1.21, anything greater, that means we want 1 minus to get, because we only go to the left. So that's 1 minus the probability of less than 1.21, which in our chart, that's 1 minus 0.8869. 1 minus that is 0.1131. So 11% of the men are going to be taller than the shower head. Now, how would I have done this in the calculator? Well, 1 minus the normal CDF of, again, our smallest number from 1.21, because we just changed him to 0 and 1. And again, that's 0.1131. So our answer, either way we do it, is 11.31% of the men fit this criteria. All right, now this one's about IQ scores. The graphs depict IQ scores of adults, and those scores are normally distributed with a mean of 100 and a standard deviation of 15. That's on the Wechsler IQ test. Well, we know that that is not a standard normal deviation, or distribution. It's just a normal one. So we have to go through and use our calculator to change this. But you know what? We've been practicing on our calculator all along, and I'm going to just use, again, we're given the areas. So why don't we do that with the calculator? We're going to need to go backwards. We're going to do inverse norm. And I'm not even going to use the formula this time because I'm going to put in what this one's standard deviation and mean are. The area is 0.9918. And the mean is 100. The standard deviation is 15. And it's to the left. I'm going to use the calculator for what it's meant for. I don't have to use the table. I can, but I don't want to. So that's 135.998 for our inverse norm or our x value down there. Our next one over here, I'm going to do him. Okay, again, I'm going to use the calculator. So I'm going to do inverse norm. And the area in this case is 0.1587. Again, 100, 15. And look, this one's to the right. I'm going to use that on the calculator. We haven't used that so far because we usually have to convert everything to the left for our charts. But why use the table when you can use the calculator? 114.997. Down here, inverse norm. So I'm again given the area. And the area is 0.9798. 100, 15, and this one's also to the right. And that's 69.255. So I found the IQ scores. If 99% of the population is less than 135 IQ score, the other one, 15% of the population is above an 114 IQ score, and 97% of the population is above a 69 IQ score. That's what these are telling us. Another example. This one says that we're going to use this data in the table for adult males and females based on a survey. And number 13, find the probability that a male has a back to knee length less than 21. So we want the probability that it's less than 21, and this is for a male. And this is, I'm going to just use the calculator, so normal CDF of my smallest, you know what, that's not enough room to write that in. So I'm going to put it down here. And this is the normal CDF of my smallest number. And I'm going to 21. And my mean for men is 23.5 according to the table. And 1.1 for the standard deviation. Put that in the calculator and I get 0.115. That's the probability that men have that. Now, a female that has the greater than 24. So probability females is greater than 24. That's again the normal. Well, it's greater, so 1 minus the normal CDF of negative 99999 to 24, 22.7 in the table, 1.0 in the table for females, and that's 1 minus 0.968, which is 0.032. So there's not very many females that are above that. Now our next one, probability of female is between 22 and 24. So probability 22 to 24 is the normal CDF of 22 to 24. Female, again, is 22.7 and 1. Put that in the calculator, and you get 0.6612. So a lot of them in the 22 to 24 range. Okay, this one says we're going to design an aircraft cockpit. When you're doing that, one of the common criteria is design it to accommodate 95% of the population. 46% of the women satisfy the height requirements for the U.S. Air Force pilots. What would be the maximum acceptable height of a woman if the requirements were changed to allow the shortest 95% of women to be pilots? So what we're doing is we're assuming the heights of women are normally distributed with a mean of 63.7, a standard deviation of 2.9. So we need to know the maximum allowable height, and should we have a minimum requireable height. Okay, so according to this, we want 95%, and we're looking for that height. So the inverse norm, because we have the area, 95%. And we have 63.7 is the mean, 2.9 is the standard deviation, and we want the left because everybody's going to be shorter than this. So that's 68.5 inches. That's what we're looking for our maximum height. Should we have a minimum height? Well, that's kind of, a up to you kind of thing. Obviously, you need to have some minimum height because you need to have enough room for the women to be in the cockpit. They are going to be more than, or they are going to be smaller than men. So I think we should have a minimum height requirement because you don't want to have the women not be able to reach the controls and things like that. All right. This one says we're looking at significantly high, significantly low. So again, we're going to be checking that out. Assume that women have a normally distributed pulse rate of a mean of 74, standard deviation of 12.5, and we're going to be looking at whether they are significantly high or significantly low. Where are those at? Well, we know our mu is 74. We know our sigma is 12.5. And we know significantly high, significantly low, that's like 5%. That was our little criteria before. It was the 5% rule. So we're going to do the inverse norm. Of 0.05, because we're going to change that to an area, of 74, 12.5, and to the left. And that tells us that that small range is 53.4 beats per minute. And then we're going to do the other way, inverse norm. Again, 0.05, 74, and 12.5. But this time to the right. And we know that is going to be 94.6 beats per minute for our significantly high range. So this one's for our low, anything less than that, and this one's for our high, anything higher than that. Now, when do we use inverse norm? That's when we are given a percent or an area and we're trying to find the z or the x. When do we use normal CDF? That's when we're trying to find the probability. Just a little bit of clues there. And this one again, back to the pilots and how long their seat, or no, these are theater seats, sorry. So for males, find P of 90. That's 90% from top, and 90% of the bottom from the top 10%. What's that critical value there? So we do inverse norm, because we know it's 90%. And the area is 0.90. And this one is for males, so 23.5 for the mean, 1.1 for the standard deviation. We're separating them from the 90% to the 10% top, which is the left, and that's 24.9 inches. That's your seat length. Again, more of the significance. We use 5% for significant values. The probability when it's greater or less than 1% makes our high or low for the probability. So we're going to do that here. And we're going to find, is 26 inches significantly high for men? That's our question. So how do we do that? Well, we do the inverse norm. Of 0.01, because that's where we're getting it from, is right here. And we're at men are 23.5 and 1.1. If we use the left, that tells us that they should be at 20.9 or less for the low. And this one's asking about 26. If we do inverse norm and do the same numbers, but for the right side, that's our higher guys. And this time we get 26.1 inches for our higher. So that or higher is high. 26 is not, so their answer is no, because it is not bigger than 26.1. So no, it's not significantly high. Okay, so our next one that we're looking at is 6.4. So continuing this normal distribution, the central limit theorem. We see that as our sample size increases, we tend to get something that is normally distributed. So we are going to call that related to our central limit theorem. So it kind of takes something that's not exactly a normal distribution, but the larger the sample size, it makes it approximately normal. So we can start using some of this normal ideas. So if we have any distribution with larger than 30, then we can approximate it with the normal distribution. That's nice. That's the central limit there. So our sample size greater than 30 means that we can approximate it with the normal distribution with a mean of mu and a standard deviation, not just sigma, but sigma divided by the square root of n. So here we are. We have heights of American women normally distributed with a mean and a standard deviation. Heights of men normally distributed, the mean and standard deviation. What's the probability that we have one randomly selected adult woman that's taller than 5'5"? Well, let's see. These are all normally distributed, they said. So we got the probability that they are greater than 5'5", that's 65 inches. And that is 1 minus the normal CDF of negative 9999, because we want our smallest number. Our mean for our women is 63.6, and our standard deviation is 2.5. And so our probability is 0.2877. So we have a 28% probability they're taller than 5'5". What's the probability that the mean height of 12 randomly selected women is greater than that? So we're going to say sigma was 2.5 a moment ago. N is 12. Mu is what X bar is, which is 63.6. So sigma bar is going to be sigma over the square root of n, which is 2.5 over the square root of 12 in this case, which is 0.7217. Now that's just using that formula we had a moment ago, the central limit theorem, approximating it as normal. So we want greater than 65 inches, so probability that they are greater than 65 inches is 1 minus the normal CDF, and from 65 to 63.6 with a new standard deviation of 0.7217 to make it approximately normal, so 0.0262. All right, Mensa requires a score in the top 2% on a standard intelligence test. The Wechsler does a mean of 100, a standard deviation of 15, and the scores are normally distributed. We're going to find the minimum Wechsler score that satisfies the Mensa requirement. So we want the inverse norm because we want the score. And it's top 2%, so that's 0.02. And it's 115, and to the right is a score of 131. If we have 4 randomly selected adults take this test, find the probability their mean score is at least 131. So to get our sigma, we're going to take 15 divided by the square root of 4, just 7.5. That changes our standard deviation. So the probability at least 131 is 1 minus the normal CDF (131 at 100, 15 there. Oh, not 15, 7.5, sorry. Forgot that it changed. And we get 0.1234 zeros, 179. So we don't have very many. We select 4 of them, find their probability that their mean score is greater than 131. That's not very many people that's going to do that. So if 4 subjects take this test and they have a mean of 132, but the individual scores are lost, can we conclude that all 4 are eligible for Mensa? Heck no. Just because their mean is 132, not all of them meet 131 score requirement. So no. Just because the mean is 132 does not mean all are 131 or above. All right, now 6.5, your last section in here. Sorry, guys, these are long notes. We're going to look at normal quantile plots. This is actually really easy. You know about histograms. You can kind of see if they're bell-shaped to see if they have a normal distribution. You can look at outliers, and if there's more than one outlier present, you conclude that your data might not be normal. You can look at the normal quantile plot and see if it is mostly linear. So those are what we're going to do. The normal quantile plot. Again, we want to see if it's a straight line pattern. If it's not a straight line pattern, then we say then that it's not going to be our normal distribution. We also want to make sure that they don't have some systematic pattern, like looking like a, say maybe an exponential curve or something. So again, it's picture looking right now. All right, here is a bell-shaped curve approximately for your normal histogram. So this guy here, the histogram is normal. He checks out. This guy, look at this. It's mostly a line. There's a little bit of outlier, but not much. Mostly a straight line. So these are normal. Okay, now this one here, when we look at him, he is kind of this little pattern going on that's kind of a curvy. So he is not a normal distribution. All right, this shows a skewed. So this one is not normal. And then look at his little pattern. He's kind of logarithmic if you ask me. So not normal. All right, so you take a look at this one. This one's a normal plot or normal quantile plot we tried to do. Is this a normal distribution? Yes, it's normal because it makes a straight line and it's no other pattern. Okay, let's take a look at the next one. Again, this one's mostly normal. So yes, this one's a normal. He's mostly a straight line, not making any weird patterns. This one, look at him. He's kind of got a log-looking thing, so he is not normal. So does this dude. He's really looking like a log. He's definitely not normal. Now you get to go practice all of